Baccari from ICFU, and he will talk about Bell correlations depth in many-body systems.
Thank you. I would also like to thank the organizers for giving me the opportunity to present this result. So I'm going to talk about a project that we started quite some time ago. It was when most of the authors were at ICFO, and then it passed long enough time that it became magically a collaboration between 4 institutions. So in short, the question we ask ourselves is, can we find an efficient way of witnessing how many particles in a big system are sharing non-local correlations in a way that is using only partial information, so in situations where only partial information about the system is accessible. And well, the spoiler is that yes, we can do it. But first of all, so why do we think this is an interesting question? Well, in the last years, we have been witnessing a lot of interest in building larger and larger quantum systems. And I think a paradigmatic example is the case of quantum computers. Now we have basically all the most important tech companies that are like racing to get the biggest system and compete with each other. But it's not only in this case, but also we have also other platforms like ways to trap atoms and ions. And now we are able to produce and control with given like different degrees of precision systems that range from the order of tens to order of some hundreds of particles. But okay, now we have a very large system, a quite big system. And one important question is how quantum is this system? And a very natural way of asking, well, or answering this question would be to say, is it entangled, for instance, or is it able to produce non-local correlations? And since we're talking about a large system, actually it's even more interesting to quantify this question. So to ask, how many particles can we really say that they are entangled or are producing non-local correlations among each other? And now, okay, a standard approach could be, let's just estimate the state of the system. But this is something that, for instance, with tomography is impossible in practice because it's for a generic state, it requires an exponential effort with the number of particles. And so what we need is something that has requirements that scale efficiently nicely with the size of the system. And at the same time work with partial information because we generally cannot measure any kind of observables or we cannot estimate the whole distribution produced by a system. And we go to the limit, the extreme limit, in which when a system is large enough, we can basically only measure particle number or something like that, which boils down to measuring collective spin components, basically. And so in such a framework, and with such limitations, what can we say about non-locality in the system? And why, okay, first of all, well, before going to the framework, why do we focus on non-locality? One main motivation is the device-independent approach. So we want something that works as a black box, but also, okay, non-locality implies entanglement, but it's stronger than entanglement. There are entangled states that don't produce non-local correlations, and it's also something that is not yet very studied in the context of many-body physics. So who knows? Maybe it can like shed some light in some properties of many-body systems. So what is the theoretical framework? Well, we had quite some talks on Bell correlations today. So, well, the main difference here will be that we have a multipartite scenario. So the idea is that we have many parties, and each of them has access to one of the particles. And it can choose inputs that correspond to some measurements, local measurements, and collect some outputs. But then the only information we care about or we study is this distribution of given outputs, so the resulting outputs given the inputs that were chosen. And so, as in the bipartite scenario, if this distribution is described by a local model, so when we have shared randomness and some local response functions, the correlations are classically produced, and so they are said to be local. And whenever this is not the case, we witness non-locality. But then, as I was saying, we actually want to make this question more quantitative. So one important notion is this of non-locality depth. So for instance, let's imagine that we have a situation in which we have two of the boxes that are two of the particles that share non-local correlations. So this could be, for instance, described by this hybrid model in which there is a bipartite distribution that's non-local, the rest is locally correlated. So clearly the resulting distribution is non-local, but it's not the most non-local it can get. No, it's sort of bipartite. And then of course this is the same if we have other groups of two particles. So the non-locality depth is basically the size of the biggest subgroup of particles in my system that are sharing non-local correlations. And it goes a bit as a hierarchy. We can have a case in which the biggest size is 3 and so on up to the ultimate limit that is the most genuine form of multipartite non-locality when the depth is the same size of the system. And it's very useful to study this in a geometrical framework. So, well, okay, we basically take our correlations and we see them as a point in a geometrical space. So then we can define the set of all the points that would correspond to distribution that are local. Similarly, a slightly bigger set is the quantum produced by measurements on quantum states. And the no-signaling is the basically a bigger set than the quantum, and it's all the correlations that are constrained only by the fact that the particles cannot signal to each other faster than light. And okay, so the local set is, for instance, a polytope, which means that it can be described by equivalently by a finite amount of extremal points of these vertices, and also by a finite amount of facets, so of inequalities that are satisfied by any point inside the set. So this is geometrically basically what is a Bell inequality. When any point that is non-local will violate one of these inequalities, and so we can use this inequality to witness non-locality. So how does this non-locality depth come into the picture? Basically, we can now introduce other sets in which, so imagine all the correlations that are produced when we allow for groups of at least two particles to group together and share non-local correlations. Here, we could choose the resource, we allow them to share up to no-signaling correlations, so something that is a bit more than quantum. And then if we allow groups of 3, then up to 3, we get a slightly bigger set, and we can go on up to the ultimate, like to this n-1, basically. And the nice thing is that since we assume that the resource that is used is no-signaling, all these sets are polytopes as well, and so we can characterize them by listing all their extremal points that are constructed by combining vertices of the local set of the no-signaling set. And in particular, whenever we want to characterize depth k, we need to know the vertices of the no-signaling polytope of k particles. And again, well, now imagine we know all the vertices, we couldn't get the resulting inequalities, and any of them is a witness of no-locality depth. Why? Because if I violate this inequality, it means that I cannot be described by a model that allows for groups of k particles, which means that there are to be at least k+1 particles that are entangled. Okay, this is potentially nice, but it's very hard to study as a problem in practice and in general. Why? Well, there are mainly 2 reasons. First one, okay, I was saying that we want to characterize the vertices of the k-producible polytopes. We need to know, to do that, we need to know the vertices of the no-signaling polytope. So this is clearly, in practice and in reality, not as simple as I was drawing. It's a very complex object in a very high-dimensional space, and it's generally described by an exponential amount of inequalities. And what we need are actually, we need to move to the vertices. We need to know the vertices from the inequality. And this is known in the simplest cases for 2, 3 particles, but of course we want to say something a bit more for a bigger size. And there is no way to tackle this in general. And then, okay, imagine we found a way to get all these vertices of the no-signaling polytopes. Now we want to know the vertices of the k-producible ones. So already for the local set, we have an exponential amount of vertices. This gets even bigger if we have k-producible polytopes. Now we want to go to the other pictures, we want the inequality. And this is as difficult as the previous case, even if not worse. Okay, but I was saying that we don't actually want the general picture. We adopt a framework that uses this notion of partial information. And the framework we adopt is this symmetric two-body correlations framework. So now I couldn't describe my whole distribution in terms of these correlators of higher and higher order, like 1-body expectation values, 2-body, 3, up to the full body. And this is an exponential amount of information. Again, it's the content of the whole distribution. But now, so what we do first is to symmetrize. So we take actually the average of the permutation of the parties. So SL is basically the sum of all the expectation values of the measurement L. And so it's the same for all the others. So SLM is just the sum of possible pairs of the correlators in which one party is measuring L, measurement L, and the other measurement M. this already reduces the amount of information, but then we also cut and we remove the higher correlations. We stay with 1 and 2. And this defines a constant amount of information. The amount of these correlators doesn't depend on the number of particles. Okay. And for instance, the simplest case is when all the parties can choose only 2 possible inputs. So in this case, we have 5 quantities. And in this framework, we look for basically Bell inequalities. So in general, linear combination of these 5 quantities, whose violations that are satisfied by any correlations that have a depth k. So violating this inequality will witness depth of at least of k plus 1. And it might seem very simple, but actually this is a framework that was already introduced some years ago. And it's possible to, so it was answered already the question whether this is possible, like this inequality can detect non-locality in the standard scenario. This is one example of an inequality that is valid for any number of particles. And it can be used, like there are quantum states that produce correlations that violate this inequality. Okay, so time to move to the results. First of all, okay, how does this reduction actually simplify? Yes, yes, I go back. Here, yes. Next one, yeah. Basically, well, this would be the simplest model. So now you test against the fully local model. So if you violate this inequality, in principle, you don't know. It could be that you have 2 particles in your system that are non-local and the rest is just factorized. Yes. Yes. Mm-hmm. Yes, yes. Because you involve, like, it's 2 body, but you combine all the pairs, no? So potentially you access all the combinations. Yeah, okay. So first answer is yes, the problem does become easier in this framework. And geometrically, again, so now basically we take our very complicated k-producible polytopes and we actually want to study them in a very smaller space, like parameterized by these 5 quantities. And this operation is basically a projection operation. And then we want to characterize these polytopes. So I was mentioning before these 2 problems, characterizing the vertices on a single polytope and in general the k-producible one. So let's see the second one first. So basically the simplification here comes from the fact that we are averaging and all the permutations. So basically there is a lot of configurations or scenarios that are equivalent to us. Like basically the only thing we care about here is to know, where is the pointer? Ah, yeah, here. To list, like to see in this case all they will look the same because we just care that one pair is shared single in correlations and all the others are local. And so many others are, for instance, here it will have that 2 pairs are shared 2 potentially different sets of in correlations, like corresponding to the different vertices. But in general, we just need to list all the possible choices of assigning like these pairwise boxes, all the different ones that correspond to the different vertices of the non-single polytope, and the local ones. And we need to choose all the possible assignments, like of this counting of boxes that sum up to the total number of particles. And this is polynomial in N. And the example of k equal 2, but it works for any k. And then, okay, what about the vertices of the polytope? So we need to know the vertices, again, not in the space, but in the projected space. So if we manage to characterize the projection of the non-single polytope, we know all these boxes, and we can list this polynomial number of vertices of the k-producible polytopes. So one can divide this projection into 2 steps, and this makes it easier, actually, because we can first, as I was showing before, symmetrize, so still keep all the full body and then symmetrize, and then cut out the higher order. So now, again, okay, the non-single polytope is described by inequalities. So projecting with inequalities is very hard. It's something extremely costly. But the nice thing is that in this first step, we can prove that projecting is equal to intersecting. It's a quite technical result, but what it means basically is that this first step can be done very efficiently. And then we just need to perform the second step, and this is still costly, but it has to be done only on quadratic number of terms. So Okay, what does this mean in practice? It means that we are able to find all the vertices of a single polytope up to 6 particles. And this allows us to completely characterize the problem of this witnessing non-locality depth for depth that is smaller than 7, and for particles that are in the range of up to 15 particles. So if you have a system of intermediate size and you want to know up to, like, if there are at least 7 particles in your system that are sharing non-local correlations, and you want to do it with partial information, there is a complete list of inequalities that you can try to test. But then, okay, the question is, what happens, like, can I do it for any number of particles? No, okay. First, okay, so an example, just to see that it's also interesting in practice, because this is an inequality that works for 5 particles, and it detects generally multipartite non-locality. So it will tell you that they are generally non-local between all of them. And it's actually violated by a quite natural state, the W state. So one might say, okay, it's a very abstract and result, but potentially one can use it for physically relevant states. Then, okay, as I was saying, what about like more particles? We focus on the inequality I was showing before, so this will have a local bound and a maximal quantum violation. And what we showed is actually that you can derive a bound that depends on the non-locality depth. So now you will have a higher bound if allow, for instance, for up to 3, it's same as the local. But then we get some sort of hierarchy of bounds, which imply that basically you can just measure the same inequality, and depending on how high you score in this ladder, you can certify, for instance, here that you at least more than 5 particles were non-local in sharing non-local correlations. And why do we care about an inequality that works for any number of particles? Well, because it was also interestingly noticed in previous papers that one can estimate this symmetric 1 and 2 body correlations with collective measurements, collective spin measurements. So one can connect inequality to a witness in terms of these collective spin components. The price you pay is that you lose the device independent assumption. You have to make this connection, you have to assume that you're making spin measurements. But then one can apply it to experimental data. We took the data from a previous experiment of a system of roughly 500 particles. And we could see that the point they get actually can be used to certify more than simply non-locality. You can certify, well, okay, depending on how you look at this error bar, maybe between 5 or 6 particles that are correlated. Okay. So to sum up, the question was, can we detect non-locality depth? So how many particles are entangled in our system with 2 body correlators with very partial information? The answer is yes. It's yes for intermediate size system, also for large size system, and potentially we can also use these witnesses in many body experiments already now. Where can we go forward? Like, okay, very briefly, so one could ask, okay, you focus on non-locality, but one could say, I'm fine also with entanglements. Like, I want a device independent test, but I don't want to know about non-locality. I just want to know if my system is entangled in some way. And one can do a similar study of this problem with this kind of inequalities and framework. And well, if you're interested to know more, you can read it's on arXiv, this paper. And then the other is, okay, so in the end, we witness non-locality depth for a quite small number of particles. Like we can go up to 6 or 7. And this is mainly, so the main bottleneck is projecting this non-single polytope. This is the real problem. So what we started studying with a master student in ICFO, Victor Lopez, was an idea, okay, maybe we don't need to project the non-single polytope, we can approximate it from outside, and maybe we get an efficient way of projecting this non-single polytope, and go for a higher number of particles, so get a way to witness non-locality depth for higher numbers of particles. And it seems, well, we have very preliminary results, but it seems that it works, and actually we have a guess for an inequality that is able to detect genuinely multipartite non-locality for any number of particles. Okay, and well, of course, another very interesting application would be to apply these inequalities in other experiments with different platforms. And with this, I conclude, and I thank you for your attention.
questions?
So in your definition of k-producibility,